Hello and welcome to today's webinar on IR detector spectral filtering. My name is Desmond Lamont and I am a director with Teledyne's FLIR and FLIR Science and Research vertical. Today is going to be the final webinar in the series covering the 5 things to know about IR detectors, specifically for research, development, and scientific applications. Before we get started, I did want to invite you to enter questions through the webinar chat. I'm going to go ahead and try to answer these as time permits, but rest assured we are going to try to get to all of those. If not, we'll follow up afterwards. Brief agenda here. We're going to be, for basically the sake of brevity, we're going to do a high-level introduction of infrared with some additional depth on the 2 primary detector types as they relate to spectral filtering, which is, again, the topic of the day. And then to wrap things up, we're going to talk about some example applications. And this is it. I mean, we've made it to the end. It's been fun, and we're going to cover some more interesting information here today. But if, again, you're just joining us and this is the first webinar in the series that you're coming on to here, this is the final webinar in the series covering the 5 things that you need to know about IR detectors for research applications. It's okay, though. If you want to relive the adventure, all the sessions are recorded and available for on-demand viewing on our website. Currently, all the prior sessions covering speed, sensitivity, spatial resolution, trigger sync, those are all ready and available for on-demand viewing. So check those out, share them with colleagues who are interested in learning a little bit more about IR detectors for R&D or just in general. So what IR products does Teledyne FLIR make? Well, more specifically, what do we make for engineers, scientists, technicians like yourselves? Well, our cameras operate in the infrared spectrum, located at wavelengths longer than the visible spectrum that most of us are used to seeing with our own eyes. At FLIR, the infrared spectrum begins at around 1 micron, as you see here, with true thermal bands beginning at about 3 micron, which I'll get into in a minute. At the shortest wavelengths in the infrared spectrum, we have SWIR, which is shortwave infrared. SWIR, located closest to the visible spectrum, it's not only good for seeing through materials like glass, where we get to exploit that kind of spectral response or spectral transmission, which is something that we'll talk about today, but it's also useful for visibility through things like haze, capturing in-band SWIR spectral information, seeing through layers of paint for non-destructive engineering, non-destructive test. And I want to point out that our SWIR camera, the response of that is so linear that we can actually calibrate it for thermography, which again, it being close to the visible spectrum makes it very difficult just due to the noise floor that you have from light. So we can calibrate that, but the temperature floor for that is going to start at 400 Celsius. So a very high temperature floor on that. Next is going to be midwave. That's MWIR. This is the standard range when it comes to most radiometry high performance thermography applications. And the slope of the Planck curve here is going to enable excellent contrast. If you recall, it's got a nice vertical aspect to it there. The detectors are exceptionally sensitive at typically better than 20 millikelvin. That's 0.02 Celsius sensitivity. And for many applications, there's enough energy to adequately fill the detector wells to run at very fast frame rates. And then finally, we have LWIR, which is long wave infrared. At FLIR, that's going to be about 7.5 micron to 14. If you're talking to more space focused individuals, their long wave might start after 14, something like that. But here it's 7.5 to 14. And there are a few different detector technologies that address long wave infrared. Long wave is very interesting because there's a lot of photons out there, and that enables better measurements of colder temperatures. It also enables the use of silicon-based detectors, which we'll get into here in a moment, and it allows for cryo-cooled options that achieve extremely short integration times in comparison to their mid-wave counterparts at ambient temperature ranges. In addition, in the long wave, you can experience fewer solar artifacts, stuff like that. So there's some other goodness there. But at the end of the day, all the IR wavebands that you see here are complementary to one another for the unique capabilities or properties found in each range of that spectrum. So for those of you that are completely unfamiliar with IR detectors and cameras, you've never seen one before, On the left side of this chart, it shows common representations of the microbolometer, that silicon-based detector system. These range from very small sensors like the one in the bottom left to more common handheld cameras used by many people for quick evaluation of a circuit, motor, or other relatively larger, slower target. On the right-hand side of the chart are examples of cryo-cooled cameras. Also called photon counters or quantum detectors. These systems are much higher performance and are typically the models of choice for engineers and scientists due to their capability, their flexibility, and access to the raw data. Whereas the bolometer-based cameras on the left are only sensitive in the long wave bands, the cryo-cooled detector types actually have materials that can cover midwave and long wave, sometimes both, depending on the focal plane array material used. In the center right of this frame here, going from top to bottom, you see our cooled high definition A8580 model camera, which is available with a 1280 by 1024 resolution, and it can be had at that same resolution and frame rates options in both midwave INSBE and long wave SLS material. Below that is going to be the X series platform, bottom center, the silver camera there. That is just loaded with connectivity options and the highest frame rates, highest performance. To the far right, that's an example of our range science or RS models. These are typically used at open air test sites and other harsh environments for long range infrared captures. So it's just a very quick rundown of some common examples of camera types here. This slide here, it can get a little bit busy, but we'll get through it. The bar that you see before you, it's a representation of the electromagnetic spectrum, similar to what we just looked at a second ago here. But starting with UV at the far left and long wave infrared at the far right, as we just defined. As we move from left to right, the wavelengths are going to get longer because of the typical ranges that we deal with. I mentioned most of us that work in the infrared are going to start at 1 micron for our thermal bands. But we typically refer to, those of us that work in the infrared, we typically refer to these units of measure as micrometers or micrometers. For example, we might say that the near IR band starts at 1 micron. So I apologize to those of you that work in nanometers, but it's a fairly easy conversion that I trust that you can overcome, so I don't feel that bad. The first thing to note here is that where we consider the thermal bands to start, right? So I mentioned that a second ago. This is going to be at 3 micron, and it's due in part because reflected light really dominates your signals below 3 micron, and that contributes to that SWIR camera having to start at about 400 Celsius to read those temperatures. At 3 micron and above, the mix shifts and your black body radiation dominates, vastly improving the potential signal to noise ratio that we're trying to capture here. These are the most common detector material types found for infrared. You've got InGas or indium gallium arsenide as the most popular choice for SWIR cameras or shortwave infrared. You've got indium antimonide, which is the INSBE, there for both broadband and standard midwave. Broadband detector material for this, in this case, just means that it can get down to 1 micron wavelength and as high as roughly 5 micron. And I say roughly because the detector material and design of the total detector, and camera influence the exact cutoff of those. It should also be noted that just because a material can have a response in a wavelength doesn't inherently mean that it's the most ideal for that wavelength. For example, INSBE can get down to 1 micron, but the response isn't very good. So since we're talking about spectral filtering today, if your application had a requirement to capture data at 1 micron, discrete, I wouldn't recommend INSBE until we work through all of the other test requirements to understand where the 1 micron requirement fit in the overall priority of the capture there. SWIR would probably be a better option for that. Another popular detector material of choice has been MCT or mercad cadmium telluride. However, while it's very sensitive, it's a very sensitive material, it can be pretty temperamental to work with respect to drift. So there's a lot of updating to do those captures. So for long wave infrared, the most common is going to be the microbolometer, which is a silicon-based material. A more recent cryo-cooled material for the industry is going to be SLS or strain layer superlattice type 2. That material, it allows us to have high performance long wave infrared detectors that address some of the negative aspects of MCT in trade for just a slight decrease in sensitivity there. So that's what you'll typically see from us from a cryo-cooled long wave standpoint. So now you might be wondering, with all these options, what should I choose? That's this too. I've got option overload. Well, the good news is that the market has basically standardized on the use of InGas for SWIR, INSBE for midwave, and bolometers for long wave. Though I will say that in the long wave or any wave band, it really depends on your application requirements again to determine the specific option that you might go with here. But these are the main players. Having an understanding of the most common detector types, such as microbolometers and cryo-cooled photon counters, it's really going to help you move past the most important aspects of selecting an IR detector for your application. With respect to spectral filtering, a very obvious aspect is going to exist in how the detector material response, the spectral response, lines up with the exact target wavelength that you're trying to exploit or perhaps block. So very quick example is if you care about something that's happening at 8 micron, you can't really use an INSBE midwave camera to address that. You're just not aligned spectrally at all to do that. So very basic example there. So let's just dive into microbolometers and photon counters very briefly. We're only going to cover very basic information on the detector operation in this webinar. We've done it a lot in the prior ones. So if you're very interested in learning more, go back and check out those prior videos in the series. I highly recommend the first one that covers speed, as it probably has the deepest dive into the differences in the detector design itself, because that has a direct line there. Microbolometers, moving on, or sometimes called just bolometers, they provide the user temperature data by measuring the change in resistance over the detector element as it's heated by the incident radiation. That radiation is going to be focused onto the detector via a lens, and each pixel in the image has a corresponding detector element. You can see a magnified image of a single element or pixel in the bottom right, and the array of pixels in the top right image on the slide. So that would be your overall. So if you had a 640 by 480 resolution detector, that array in the top image would be 640 by 480 of those pixel elements there. So these detectors, they're great for typical common data captures, but they are relatively slow and less sensitive compared to the cryo-cooled options. Due to their lower cost, though, they are far more prevalent in the marketplace. If you recall from the earlier slide, bolometer detectors are sensitive from about 7.5 micron to 14 micron wavelength, and that means that they're long wave, infrared detectors or LWIR detectors, and can only be used to exploit or manipulate phenomena that occur in that part of the spectrum, like we just talked about. Unfortunately, because of the optimization and digital image processing that has to be performed on a lot of the bolometer camera types, there aren't a lot of hooks for a user to perform a lot of field modifications, even as simple as applying a filter and then doing a non-uniformity correction. There's just not a lot of hooks there. So typically you'll see a lot of spectral applications leveraging the cryo-cooled option cameras. There are some options on the bolometer side, but it's very much rarer. So cryo-cooled systems, photon counters, cryo-cooled detectors, they utilize a hybrid detector that's created by combining a focal plane array of some unique material, like we just talked about, like an example would be INSBE or indium antimonide, with an electronics package that's referred to as the ROIC, which is the readout integrated circuit. So it's just a sandwich detector of this unique focal plane array material with that electronics package. That's why it's called a hybrid detector. Those detectors, they work by cooling the detector material down to around 77 Kelvin, so very cold, in order to remove electrons from the conduction band of the focal plane material. Those electrons that are present here would conduct a current and provide a signal, and we don't want any pre-existing signal when we're trying to take measurements. So basically, the focal plane array material is very sensitive, and in order to use it for measurements, we need to control that sensitivity. And this is done by cooling the material down to an exceptionally low temperature and moving all potential electrons, or as many as we can, over to the valence band, so that when incident radiation strikes them, they kick the electron over to the conduction band of the material. We get a signal. In this case, it's a photocurrent. So if I lost you there, don't worry. You can still understand the rest of the presentation without following that too closely. With a cryo-cooled detector, though, each pixel, it's going to be a unit cell that has its own integration capacitor. So we saw before on the bolometer side where we're heating up those detector elements and reading a change in resistance. These detectors, they're designed completely differently. We're capturing that energy in this integration capacitor. So we can set the integration time to tell the pixels how long to remain open to collecting that photocurrent into that capacitor. If we fill it to the top, we get a saturated pixel. If we fill all the pixels, then we get a saturated image. Too little energy captured, and we get a grainy image. Therefore, a good proxy for integration time is exposure time in the visible light camera world. The only gotcha here is that in infrared, we can't typically add more light to get our target or scene to improve a capture that requires a short exposure time. It just doesn't work that way. Whereas with visible, camera systems, you can add a lot more lighting and decrease your exposure time and get some great image captures. For us, we're dealing with the light. So your target's energy typically dictates how fast you're going to be able to run a camera, which, kind of leads into the speed topic there, so I'm not going to follow that too hard. You don't really need to understand how these cameras operate at a low level to get the idea that these are much more sensitive than the bolometers. With these detectors, or with these detecting changes at around 0.02 Celsius, so exceptionally small changes. Not only that, but the electronics packages typically built around the detectors enable a user to access low-level settings to optimize them, and it's because of this aspect that most spectral filtering is done with this type of detector. Effectively, the focal plane array, or FPA for short, is what determines the spectral sensitivity and the response of the camera system. The indium antimonide, it's going to have a response from about 1 micron to 5 micron, but we typically filter those 3 to 5 micron for best performance in most applications. Here's a simplified diagram of a cryo-cooled detector. As you can see, the entire detector is contained within a vacuum in order to help keep it at that low temperature and not produce unwanted byproducts like ice. If you start at the top of the frame here, you'll see where incident radiation from the target scene enters the detector. This graphic doesn't show the lens, but it's important to note that lenses typically have anti-reflective coatings for specific spectral ranges, and that helps with transmission in those ranges. So a 3 to 5 micron, camera, it'll typically have a lens optimized for a 3 to 5 micron wavelength. And while the AR coatings aren't top hat curves with hardline blocking of wavelengths immediately outside of the specified range, they do affect, what wavelengths get to the detector. And depending on the intended range, they could block all the energy. For example, if you put a long wave infrared, optimized lens on a mid-wave camera, you'd likely not see anything. And that's because not only is there long wave anti-reflective coating on the material, but the actual material of the lens could be such that it doesn't even transmit in the 3 to 5 micron range. So things of that nature you have to think about. You'll learn all sorts of interesting things actually about common materials by just pointing a camera around your world. One that always seems to get people is that you can't see through glass or plexiglass, with a mid-wave end-up camera. But since you're so used to the concept that you're no longer, since you're so used to it, the concept that you're no longer viewing the world in the visible spectrum takes a minute to sink in. Glass doesn't transmit in most IR wavelengths, so it shows up as opaque, and now you see the surface of the glass. So that's where I was going with that. So at any rate, let's get back on track here. After the incident light, again, passes through the lens, it then passes through the exterior window and then through the cold filter. The cold filter is where an INSBE detector is actually filtered down to 1 to 5 or 3 to 5 micron, or where, let's say, an SLS long wave detector is filtered to 7.5 to 12 micron. And we'll revisit this soon, but this is also where you can apply another filter with some special property or response for those for those that want the most sensitivity in that specific application. After light passes through, this tighter filter, in this case 3 to 5 micron, it then passes through a chamber with some complex baffling. It's much more complex than what it shows here, obviously, and ultimately strikes the FPA, or focal plane array, kicking off our photocurrent into the integration capacitor. At the bottom of the chart here, you see a representation of a closed cycle cooler found in most detector systems like this today. Instead of being cooled with liquid nitrogen, or LN2, these are brought to temperature via closed cycle Stirling engine helium is what powers that. So that concludes reviewing the IR detectors. Let's get into wavelengths and detector responses. So here's a chart. It depicts wavelengths that are IR friendly, or rather the wavelengths that have the best transmission for IR. And those are shown under the curve in a purplish color there. Nice Easter purple. If there's enough atmosphere between you and your target, it has a strong likelihood of attenuating your signal, especially if that air path has a lot of humidity, dust, or heat in it. So going back to IR detectors, most of the detector materials we've discussed actually do respond to wavelengths in the 5 to 7 realm. But as you can see here from the chart, this is a veritable no man's land for IR transmission. So you might wonder what's going on in that 5 to 7.5 or 5.5 to 7.5 kind of range. And that's really where the water vapor exists in the atmosphere. There's just a lot of water vapor in that 5 to 7.5 range there, and water vapor absorbs IR energy a lot, and that's why you don't see transmission there. And so how do we deal with it? Well, if you remember from the cooled detector diagram, we applied a cold filter that cuts off sharply at around 5 micron for mid-wave detectors, and at around 7.5 micron to start the long wave band. So that's how we get around it. This is really the most basic and most common example of applying a filter to manipulate the spectral response of a camera, with the endpoint here not being to exploit some specific material or target in the scene, but to avoid noise from the water band in the 5 to 7 micron range. And here's what that would look like if we took that 3 to 5 micron cold filter and applied it. This is what we would see in terms of response. It would block off a nice, fairly good top hat there with some great transmission in the desired, 3 to 5 range or so. And you might note there that, here, let me just back up one. You might note that there's this gap at about 4.3, 4.4 micron where it drops, and that's CO2 that's in the atmosphere. So some of our customers that like to do long range applications, like with the RS model camera that I showed earlier, will have us build the detector with a CO2 notch filter that blocks off that specific realm so that they don't get that noise in the system. So moving on, the exact spectral response that a detector has is very detector specific. For the vast majority of applications, typical detector responses that are representative of a given detector model, like you see here, they're extremely useful for things like considering options for spectral filtering, selecting an IR window material for an environmental chamber or blast chamber, something like that you need to view through, and you want to make sure it's compatible with the camera that you're using, or performing custom calibrations and so on. Here you see a typical response curve of a FLIR 3 to 5 micron mid-wave camera on the left. As you can tell from the curve, it has a fairly flat response across the 3 to 5 waveband, so not much more to say about that. The chart on the right is a typical SLS long wave IR response. This is covering 7.5 to 12 micron, and as you can see, it does have some ups and downs with troughs in the photon response that may or may not be detrimental to a spectral filtering application. Again, it really depends on what we're trying to see or measure, how we're trying to see or measure it, and where it falls against this chart. So if you had something that was at 10 micron, maybe you're not going to, unless it's a pretty strong signal source, maybe it's not going to be that useful. Maybe it will be. It all depends. The important thing to take note here is that detectors do not all have top hat responses. And depending on your explicit requirement, the success may be more challenging than you initially thought. But hey, that's science and research in a nutshell, right? As a side note, since I bring up typical response curves, we do post our response curves to FLIR.custhelp.com. So that's our support site. And it's a great resource for everything from user manuals, mechanical drawings, questions and answers, and these charts. So if you need access to these, FLIR.custhelp.com is where you're going to want to go. So before we bring this concept to the real world, with some examples, I'd just like to show the two methods typically deployed to perform spectral filtering. These are the warm filter and the cold filter. So I mentioned in the diagram for the cooled camera that we applied this 3 to 5 micron, cold filtered to make it the most sensitive and locked in. So if you look at the right side of this chart, you see that those filters become part of the detector. Again, they're cooled down to temperature, so it's 77 Kelvin. And really the point here, the way that you get more sensitivity out of that is that because it's cooled down to the same temperature as the detector, now we don't have radiation from that filter. And that's really the main point between a warm filter and a cold filter, is that a warm filter is not chilled down to the same temperature of the detector and inherently is providing radiation of its own. So it's going to add a noise floor to your signal. And so the more narrow that bandpass gets, let's say that you want to apply a really narrow bandpass and your target scene that you want to, or target event, phenomena, whatever it is you want to look at, is very small in terms of signal, it's going to be extremely difficult to capture that, specifically because of the fact that you've added noise to your signal by putting in that filter, that warm filter, and then you've also only provided a very narrow window for any energy to get through. So that's the best way to think of it, is that it's not that you can't use warm filters. Many people use warm filters very successfully. It's just you have to consider where you're looking in terms of how your detector response lines up with the event or phenomena that you want to see, and what that energy level might look like. Now, you can always crank up the integration time, or exposure time, so that you're capturing for a longer period of time, but it all depends on what kind of noise floor that you're also going to add to that signal. So a cold filter, it's going to be forever part of that detector. Most companies, most people will not attempt disassembling those, because you stand at a high likelihood of damaging the overall detector and having to scrap it, and they're very expensive. So consider those purpose-built forever, but the best performance for those specific filterings applications. And then the warm filters, this is where you've got flexibility. And these are going to be installed again outside of the detector. They'll typically be they're typically 1-inch filters. They get put in a filter holder that maybe screws into the back of the optic, or they get installed in a motorized filter wheel. They're interchangeable. Again, they add noise. Now this is specifically for a closed cycle Stirling setup here. So you see the example camera there. I showed earlier an image of an LN2 pore field doer camera, where, here, let me just go back to it really quickly here. Right there. So this guy here on the left-hand side. So with these, the whole reason why a user might decide, a researcher might decide to use an LN2 pore field doer, is that they're a little bit more flexible in terms of there's a lot more maintenance to them. But if you had a research project, or you were doing something where you really needed to swap out detectors and swap out different cold shields and things like that regularly, this would be a better option, because of the fact that it's not permanent, but you are able to cool everything down to temperature. That said, again, there's a lot more maintenance to it. You can't just put it in any position. And it's really only useful if you've got a bunch of, focal plane array, readout integrated circuit sandwiches, and all of the filters that you need, and you were very well versed in that. From a usability standpoint, closed cycle is much better. Let me get back to where I was now. Okay. So applications and considerations. So let's talk about through flames. And the first example, we have a researcher that was interested in a visual confirmation of the combustion of coal particles within the flame for burn efficiency. So they wanted to see these coal particles burning up, but the flame was in the way. And that's a pretty common application. I mean, they also wanted to perform, once they were able to see through, if they could see through, they wanted to see the size of those. And you could do spatial calibrations with our software and take measurements by drawing a line or shape on that element and say that that is 1 millimeter in any square, or what have you. So again, seeing through flames, it's a pretty common application. And we have camera systems that leverage both custom cold filtered detectors for that purpose-built ease of use, somebody looking in a furnace or something like that regularly, as well as flexible systems that leverage warm filters placed behind the lens or in a filter wheel. That's where you'd see more on the science and research side, where someone has a specific application that comes up, some requirement where, let's say, they want to see how a material reacts within a flame. Maybe it's a munition, maybe it's some energetic, maybe it's a piece of steel or what have you, and they just want to be able to see through the material, see through the flame to see how the material reacts, and they don't want it forever that way. This application, it makes use of a 3.9 micron narrow bandpass filter that is going to exploit, where many flame types become apparent. So here's an example response curve of the off-the-shelf filter from Spectral called the BP 3900-200. And that name, it just means bandpass, that's the BP, at 3.9 micron, that's the 3900, plus or minus 200 nanometers, and that's where the dash 200 comes into play. So it's pretty easy to understand their nomenclature here. And as you can see, this filter is going to block everything outside of the target 3.9 micron plus or minus threshold range. Taking a look at the data imagery that you see on the right, you can clearly see the particles as they're burning up. On the left-hand side, you have unfiltered flame, and on the right-hand side, you see the filtered image. So now we can actually see some particles much clearer as they're burning up, which provided some great insight to our researcher. In this example, we had an engineer that needed to measure the temperature of polyethylene film to ensure some consistent temperatures were maintained while rolling PVC pipes. And without consistent temperatures, the resulting pipes, they're going to have quality problems. They're going to have delamination. They're going to have voids, cracks. So he needed to make sure that the film was maintaining a proper temperature. Now, most plastics that are relatively thick can be opaque in IR wavelengths. And inherently suitable for some temperature measurement. But thin plastics, they're very transmissive. So most of the signal that you capture is from the background or behind the target material. For example, if I put my hand or head in this image inside of a typical, plastic shopping or garbage bag, you'd be able to see it quite clearly. Thanks to our friends at Wired Magazine from back in the day for this one. In order to suppress the transmission that occurs here, and make the material more opaque, we first needed to see where the material might naturally possess a drop in transmission that we could then exploit or manipulate with a filter. Our friends at NIST, if you're not familiar with NIST, which everyone on here might be, but if you're not, they do a lot of measurements. And our friends there are always a great resource as they've characterized a lot of materials. So if you just go to the NIST website, you can look up almost any material, and they've done a lot of characterization to it, and including polyethylene here. And they even include IR spectral data in their characterization. So you can play around with that and see what that curve looks like for transmission and absorption. So after reviewing the IR transmission curve, we identified the least transmissive area. It's roughly 3.4 to 3.6 micron that you see here in the chart, and found a matching 3.45 micron narrow bandpass filter to apply. Now, if you aren't sure if the material is opaque enough after applying a filter of some kind, you're trying, let's say it's this kind of application, you can always place some object of known temperature on the other side of the material to understand what that transmission looks like. Ideally, this is going to be a calibrated black body, temperature source that you're going to use, but really anything that has a pretty stable temperature you could leverage if you weren't too concerned about a very, very explicit absolute temperature reading. With this filter material applied, we were able to achieve the opaqueness that was needed and measure the temperature of the plastic for the user, so they were able to correct their system there and make sure everything's good. Oh, and I will say that similar, I mentioned, putting a black body on the other side or some calibrated temperature source. It's very similar when you want to see the transmission of even an IR window, or maybe you want to see what the transmission air path looks like if you're looking at some distance out in the open air. So if you're out in the field and you want to see something, that's let's say 1,000 feet away or something like that, or 1,000 meters away or something like that, like you could put a known temperature source at the far end, as long as it's large enough that you've got a decent number of pixels on it. You could then measure, because you know what that temperature value actually is because it's a calibrated source. You could tell what that transmission path looks like. Same with this material here if you're trying to make it opaque. Same with an IR window if you want to know how much transmission loss is occurring when you're looking into that chamber. You can do that way as well. So optical gas imaging. this is such a great use of spectral filtering that we built an entire business unit out of it for the oil and gas industry to help them identify and repair gas leaks at refineries, wells, related sites like that. In this example, the product designer was doing some R&D testing on a new mask for administering nitrous oxide to patients. There had actually been some complaints from the dentists, doctors, and nurses that they might be feeling the effects of the gas, which none of which you want to have loopy on inhalants while working on you. In the video on the left, you see the original design, and as expected, from the feedback, there is a lot of leakage occurring. Not only is this dangerous for the medical staff, who's working on you, but it makes it challenging to know the dose that the patient is actually receiving, and not getting enough nitrous before surgery, also very terrifying from my perspective. So after being able to image the problem areas of the design, it was respun into the ladder design on the right, which you see here. And this is a much more efficient and effective design. And if it weren't for her blinking and moving around in the very slight, hint of gas leak, I'd say that the video wasn't playing, but there it is. Complete improvement over the original design. So what about comparing a common target scene with a couple of IR options to see how they perform? Here we have an exhaust pipe. This is just a static image, but I'm about to go over to Research Studio, which is our software platform here. But just to get it, set the scene here, we have the exhaust pipe of an old Dodge Ram diesel pickup truck that we're taking a look at with a CO2 filtered A6783 model camera in the top left. This is going to be a warm filter in the behind the lens there. This is an INSBE 3 to 5 micron camera that we just put a warm filter targeting where CO2 becomes opaque. On the top right-hand side, we've got a, let me just start building this here. On the top right-hand side, we've got just a standard A6783. On the bottom left, we have a purpose-built gas finder GF343 camera with a cold filter for CO2 detection, and you can see it's a handheld unit, so it's used in the industrial side for them looking for any kind of CO2 leaks with optimal usability there. And then we just have a standard build A700 microbolometer camera on the bottom right-hand side with a response of 7.5 to 14 microns. So not filtered. The two cameras on the right are not filtered explicitly for anything in the exhaust there. So we'll just take a look at that in action with the new Research Studio 3.0 software application. Let me just end the slideshow briefly here. So you should all be able to see my screen here. This is the new FLIR Research Studio 3.0 software. As you can see here, we are going to be streaming 4 different videos at once that we captured. Go ahead and hit my hotkey here. So we can go ahead and start all of these videos, and you can see what's happening. You can set up the hotkeys to specifically start the playback at the same time. And you can actually set those specifically for whatever you want it to be. They're adjustable there. You can also build out these workspaces however you want to, and then save them. So right now I've got all these. You can zoom in, that kind of stuff. So very, very flexible, very, very powerful software here. You can also change the color palette on these. Right now I've got 1, 2, 3, 4 apply, but if you wanted to change the scaling, you could as well. So again, very, very powerful software here. Again, on the top left, we've got this A6783 with the CO2 warm filter. I can do some level and span adjustment here to try to highlight it a little bit more, make it a little bit more visible. You can see it gives me the warning that I've switched to manual, which is fine. Again, this is that warm filter mid-wave camera. You can see the exhaust pretty clearly here. And I'm going to go ahead and apply a region of interest, just a line. Just put that across there. And then I'm going to go ahead and look at that in a line profile chart. I'm just going to throw that on this chart here. So here we can see the temperature value readout. So this is the apparent temperature of what we're looking at. Obviously, this is just some gas imaging. We're not actually reading any kind of accurate temperatures of this gas. Gas is not completely opaque, and therefore you can't read the surface temperature of it. There's a lot of things you can do to try to, but it's an extremely difficult problem that comes up. So this is all about imaging the gas, not really measuring it, but the apparent measurement will give us an idea of what's going on here. Again, this was that warm filtered option here. On the right-hand side, this has no filtering, and you can actually still see some of that exhaust coming through. Remember how I showed you earlier the response of a 3 to 5 camera? It had that drop in transmission where CO2 is. Remember that? That's what we're seeing here in this exhaust, because there is a lot of CO2. I'm going to go ahead and add another line on this guy here, because eventually I want to compare these. And then, you know what? I can't have them all being the same color, so I'm going to go ahead and change the color on this guy. He's going to be pink. And then what I'd like to do is not only see it, but let's compare it with the other first readout here. And then I'm going to go ahead and adjust this, because one thing to note is that when we look at the values here, I had to use 2 different scalings because, again, we applied a warm filter here. And remember how I told you that it adds its own radiation? It also narrows exactly, this is targeting exactly where CO2 is going to absorb. So it's just that small range. So remember how I talked about when you apply a filter, you knock down the energy that you can capture? Well, you see the result here in the fact that our highest temperature that we're reading, our parent temperature, is around 26 Celsius. But if you look on the right, the completely unfiltered camera, or 3 to 5 broader, filtering camera, where we're capturing all of that in-band energy, it's reading up to 73 Celsius in the scene. And that's that exact, result of applying a filter that is very narrow. You're limiting the energy that you can capture, so the overall apparent temperatures are lower. So that's just something to take note. Down in the bottom left here, we have our purpose-built camera, right? So this is the one that has a custom cold filter applied to it. So you can see that with that handheld camera, you get maximum visibility of what's occurring here. And it's in a portable format, so very useful there. And on the bottom right here, not really seeing a whole lot. This is that A700 bolometer camera system that operates in 7.5 to 14 micron. It's not filtered for anything. From a CO2 perspective, there's just not a lot to going on out there in that part of the spectrum. Now, there are other gases that we have actually taken the core of what's in the A700, put that in a handheld, and done a lot of digital image processing and some additional filtering in the lens to build a portable camera. I believe it's for methane, but the GF77 model camera. That is the only bolometer that I'm aware of that we have that anybody really has to target that kind of range, because it is so difficult to leverage those detectors for that. But that gas specifically has something that can be exploited in that 7.5 to 14 range, and that's what's important. Another thing known about gases is that we get asked sometimes about noble gases. They'll say, well, can I image this noble gas? Well, noble gases inherently aren't connected to anything, so they don't tumble, so they don't absorb, and so we can't actually filter to see noble gases. So that's just a side note there. But if we wanted to, just for fun, since we're here, let's go ahead and add some more lines across these, and we'll do some comparison across all of those. Now, these lines aren't going to be the exact same lengths because I am not that skilled, but we'll do our best. Got some anchor point in the wall there. Okay, so now I'm going to go ahead and change the color of this one. We'll make it green. And then we're going to go ahead and make this one gas finder camera. Go ahead and make that one brown. Okay, for some reason it's not clicking on that. Okay, so we're going to go ahead and just add this one to the chart in the top left. Okay, that didn't quite work out the way I intended. Let me go ahead and actually apply this chart, and then I'm going to go ahead and add it. There we go. Okay, so that one doesn't have enough response to really show up. But as you can see, the two cooled options, the pink and the green, or the two filtered options, are showing up fairly similar there. But overall, pretty useful to be able to compare some things here. You can actually also just change the name of it. So if you just wanted to say that this was called, the CO2 camera comparison or line profile, you can go ahead and adjust these and then save the whole workspace if you wanted to. So very useful there for this application. But you could also stream multiple cameras if you wanted to, so you don't have to just to compare recordings. You could compare recordings against a live image. You could compare multiple cameras against each other, or just do multiple recordings. So it's an extremely powerful tool there for us to leverage. Let me just finish building this and move on. And this brings us to our final example in spectral filtering. It's going to be target signature research. And because all objects, emit infrared radiation, the infrared is an excellent spectral region to use for object detection and tracking. Since every object has a unique infrared signature, or a fingerprint, if you will, a positive identification can be made based on that received energy. For example, a staring sensor on a Black Hawk helicopter could potentially identify an RPG, or rocket-propelled grenade, threat and respond with some countermeasure or evasive maneuver before the pilot could potentially manually react. And that's just one example. Another could be, ADS in the automotive sector, looking for, a person, or looking for, some material to avoid while driving nearly autonomously or autonomously on a city street. As you can probably imagine, the more unique the mix of wave bands, the more unique the signature, meaning that in a crowded arena or space, your system could potentially detect, identify, and then respond accordingly, and with much greater accuracy in that space. To take it the opposite direction, if you were only basing your system on a heat source, whether it be a countermeasure or a targeting system, the system may not be very robust. Especially as the arena, or let's say the field of view, becomes more contested, more complicated. For many of these types of data capture, or many of these types of data capture systems leverage both warm and cold filter models with very special and unique filters that we can't really talk about. At FLIR, we can build custom cold filtered cameras, and we do regularly with either customer provided filters or FLIR sourced filters that we work with our relationships with Spectragon, Viavi, those kind of groups, and source those for you. And we have the scale to do it fairly rapidly. Now that said, we can build custom cold filter detectors, but again, when they're part of that detector, if something goes wrong in that build, the detector material itself is damaged somehow in the build, it can go sideways. So it might take a couple extra months if something fails that way. Doesn't usually happen, but it's good to be aware if you're on a tight timeline. As an extension of custom filtering, we offer spectral response measurement services as well. When ordered, you'll receive multiple files, including the photon and power spectral response of the respective lens or camera. These measurements can be performed with specific lenses or the camera only, like I mentioned, if desired. This is very useful for anyone performing target signature analysis, because you're inherently going to be optimizing your system for the best captures. And typically that means applying the actual response curves of the specific detector to custom calibrations and other measurement techniques, rather than using typical or example curves. For those of you, if you don't know how to use a spectral response measurement, then you likely just do not need one. So don't worry about it. These are usually only important for custom cold camera work and precise radiance measurements, commonly, again, ordered with custom cold filtered cameras, and specifically more commonly in the target signature crowd. For the purpose of just comparing products, there's not really a need to pay for a response measurement. The typical responses that we can provide for free, like I mentioned on FLIR.custhelp.com, those are going to be sufficient. And even if you wanted to more accurately measure radiance with a standard 3 to 5 camera, but you're not doing that level of work, the typical response is going to be pretty good for those custom calibrations. Again, the main reason that the target signature folks need it is that it can use is because they use non-standard pass bands, and they want to document very well what they have because it directly offends their end product of that signature. And this brings us to the end of the webinar and the series. I really hope that you enjoyed it. Now let's go ahead and cover some questions in the chat.